Alrighty, so we're 1 minute past the half hour, so I guess we can get started. We've got an Astrocoffee talk today being given by Yanlong Shi from Caltech. Yanlong did their undergraduate at the University of Science and Technology of China before moving to Caltech to pursue their PhD with Dr. Philip Hopkins, which they're coming to the end of now. Take it away.
Okay, thank you. Yes, so thanks for having me. And today I'm going to talk about some updates about the black hole simulation, and especially about the Hyper-Eddington accretion in some early stage of the galaxies. Let me see. Yeah, so these are some kind of background. So the first thing is about intermediate mass black holes, because there are some formation channels of the intermediate mass black holes, but and they are also observed, but we are not sure about their formation. So there are several channels. For example, there are direct collapse and also the runaway mergers. And moreover, one very interesting idea is that there can be some stellar mass black holes that experience Hyper-Eddington accretion, which can form intermediate mass black holes. And also for the supermassive side, there are also some kind of problem about the high reactive quasars, because they are very massive, but they exist at very early stage of the universe. So this also requires some kind of Hyper-Eddington accretion. So we try to solve this problem with simulations, and we put the simulation inside a star-forming ISM to make sure that it is some kind of realistic environment. And in particular, we also want to check if there is Hyper-Eddington accretion. And moreover, in the second part of this work, we also try to consider the impact of the feedback from the black holes. Yeah, so this is a figure showing the problem of the black hole accretion and feedback. So first of all, it concerns a lot of different scales and the physics. So first of all, you have a KPC or PC scale. You have cold gas inflow from the gas reservoir to the black hole. Then when you get close to the black hole, then you can form a accretion disk. And then through the flow from the accretion disk to the black hole, you also have some kind of feedback, like you can have radiation, and also near the black hole, you can also have some kind of mass outflow in the form of jets or winds. But in the meantime, the physics dominating the process has also changed. For example, near the black hole, then you basically have the very complicated general relativistic effects. And so people have studied the possibility of Hyper-Eddington accretion with different kind of simulations, like the small scale simulations in the plot showing at the right-hand side. You can see many different simulations and also unique models. They typically assume that when the accretion rate becomes very high, then you can assume, but the radiative luminosity from the black hole is actually limited or grows slowly or sublinearly, which makes Hyper-Eddington accretion possible. Yeah, but for this kind of simulation, I typically assume that there are infinite amount of fields from the boundary condition, which is the naive necessary condition for the Hyper-Eddington accretion. But it is probably not essentially true in a more realistic environment, because the realistic ISM is always very turbulent. And so the first question, so there are then two questions. The first one is, there enough field from larger scales to make sure that we have enough fields to support the super-Eddington accretion. And second question is, what is the effect of black hole feedback? So we try to run some simulations, which is based on simulations of star formation in giant molecular clouds. So the masses of the giant molecular cloud basically range from 10 to 4 to 10 to 10 solar masses, and but they are basically grouped with different mean surface density, which we have 100, 1,000, and 10,000 So for different masses, we also have different radius. And also we try to input some black hole states. Like they can be cellular mass or intermediate black holes. Like they can be 10 to 4 solar masses. And we also have random initial velocity and position. And also, and more importantly, we are doing a monocount simulation, which does not mean that we input one black hole in one cloud, because that will be very insufficient for us to, the efficiency will be very low to produce very interesting results. So the general core is to create. Instead, we put many black holes inside one single cloud and make sure that the number of black holes will not impact the evolution of the system. And also the general goal is to create gas by gravitational capture, which is well studied or described by this kind of Bondi-Hoyer equation equations. And also we include a suite of physics called phi2, which includes many effects about the star formation, and also feedback from black holes. And there is also black hole feedback effects, but that is not included in the first part of the study, because under the condition that there's no feedback, if there are not enough field to reach the black hole, then there's no hope for hyper or super-Eddington accretion. Yeah, and so what is the so the first question is there enough field from larger scales? And equivalently, this is the question is about the impact of star formation that can on the black hole accretion, because the star formation feedback can change the status of the ISM, which is the gas reservoir for the accretion. And so there are many previous studies, like they find that the star formation efficiency is highly self-regulated by its self-gravity or the surface density, which can be described by this simple analytical argument, which we find that GM over R square is basically GM is just the G times the sigma, where sigma is the surface density. So what is the effect of stellar feedback? Then from simulations, you can find that basically it can generate many shocks and turbulences. And there are also some dense clumps in the cloud. And if the feedback is very strong, then how cloud might be disrupted. So there's all the materials are just expelled away. So these are just the different impact of the feedback, and this kind of behavior of the self-regulation of star formation efficiency also is also verified by many simulation groups. Yeah, so for the first study without feedback, then we just try to check under which condition can we expect a Hyper-Eddington accretion. So in this realization, we can try to find a lucky black hole that experienced a very significant mass growth at that time, and then try to zoom in, for example, from 50 parsec to 5 parsec, then to 0.5 parsec, and to 0.05 parsec. And we can see that when there's for this lucky black hole, when there's a very significant mass accretion, there's always a very dense mass clump near the black hole and moving in with a relative low speed, which is predicted by the Bondi-Hoyer style accretion, which is also verified in the plot. At the right-hand side, you can see that when the velocity is low and the black hole encounter a dense clump, then there's a accretion which is a little bit naive. And also, if the black hole feedback, if the stellar feedback from is very strong, then we can expect that the stellar feedback will terminate the black hole accretion early. So this is a comparison between the two different conditions with and without feedback. So we can see that if there is a strong feedback from the stars, then the material is just expelled away, which is so. And another check is for different groups of initial mean surface density, what is the behavior of the black hole accretion. So this is summarized in this plot of the cumulative distribution of the black hole accretion. On the right-hand side, you can see that for clouds with higher surface density, they are more significant mass accretion, and also we can also explain this with boundary accretion by comparing the velocity and also the velocity for the different clouds and also different radius. For example, for this one, especially for this group, you can see that there's a more overlapping between the gas bucket velocity and also the black hole velocity in its amplitude, which means there are more possibilities for them to reach low relative velocity. And also we try to check the dependence on some conditions, like initial conditions, like their masses, position, or velocity, which I think one interesting result is that because the creation process is actually very stochastic, you can see that there is very shallow dependence on the initial mass, and also there is also very shallow dependence on the position and the initial velocity or the specific angular momentum. And also we try to check the Eddington ratio, which is defined as the m dot black hole over m dot Eddington. And to evaluate the m dot Eddington, we just assume a constant radiative efficiency of 0.1. So it's just Eddington luminosity over c squared over that's 0.1 efficiency. So basically, we can find that the Eddington ratio is basically above, can reach very high. Like some of the tails can be like 10 to 3, Eddington 10 to 3, which is in the regime of Hyper-Eddington. And also we try to check the possibility of the Hyper-Eddington with some previous work. So Yanlong Shi proposed some kind of simple analytical relations for determining the Hyper-Eddington accretion based on the some boundary conditions like the density and also the temperature, and as well as the black hole mass. But they calculate this from their simulations or analytical works, which consider some kind of radiative inefficient accretion flows with feedback. So we can see that for clouds with high surface density, then basically for many black hole samples in our simulation, they are above this threshold, which ensures the possibility of Hyper-Eddington accretion, even if there is feedback. And also you can do some kind of estimation about the possibility of the feedback with this kind of boundary accretion, and also many assumptions, which maybe I don't have time to expand. And the second part is about the feedback. So we include a subgradient model of the black hole feedback. So now this is just a diagram shows the process of accretion. We include a subgradient model which includes a disk and also a black hole. So they are mass flow first from the gas reservoir to the disk, which is some kind of secondary gas reservoir, and then from this disk to the black hole. But there are also different kinds of mass or energy loss in different ways that will also deposit back to the GMC or giant molecular cloud. So we try to do some parameter survey based on this, because there are many different physical processes that we don't really understand, especially their interactions. So first we want to know what is the accretion rate from the disk to the black hole. So we just assume there's alpha disk model, and also assume that there's some kind of linear proportional relation between the disk and the black hole mass. And also for the radiative feedback, we try to include some more realistic models, like the model I showed before, that even if the accretion rate grows very quickly, then the luminosity the luminosity from the black hole is actually grows sublinearly, which is radiatively inefficient. And also there are some mechanical feedback and which are basically based on, we have two factors for this. First one is the energy loading factor, which is the and also another one is which is the energy of the jets over the m dot c square. The second one is the mass loading factor, which determines how much mass can reach the black hole and how much mass can be converted into a jet. And also there are some, and then finally there are also cosmic ray, but this is very preliminary because we want to include the ultra relativistic species of the cosmic ray and use some kind of diffusive model for this. And for this, from this kind of realization, can show that under strong radiation or winds or a cosmic ray from the black hole, then basically there's a very big difference in terms of morphology of the gas, and which shows the impact of the black hole feedback. So we'll try to use this kind of CDF to describe the creation of the black holes. The first thing we want to check is about the disk models. So we try to just naively vary the different parameters. And from our setup, they are not totally independent on each other, independent of each other. So we can find that basically these parameters, but basically we find that these parameters will affect the black hole growth linearly with their as their response, and then we try to check the mechanical feedback. So the energy of the black hole of the jet can also be described with their loading factor as well as the outflow velocity, and we found that we try to vary the different velocities or different mass loading factors, and we find that basically when there is very strong feedback, then delta MBI shows a created mass for black holes basically follows 1 over epsilon, where epsilon is just the energy loading factor of the jets, and this can be and also try to check the jet cooling time, which is quite short compared to the simulation time. So we conclude that this is basically because of the momentum outflow from the jets, and naively when there's a very weak feedback, then basically all the conditions go back to the previous part where there's no feedback. So basically this kind of relation can be fitted with this equation, and importantly we find that gamma is very close to 1, which can be also explained with some kind of momentum argument. And also for the mechanical, so the radiative feedback, we found that which is actually the fiducial result for the second part. We found that the radiative feedback actually is not very important, even when we assume there's some kind of radiative inefficient flows like these models, which we choose two different kinds of equations or forms from the literature. But we also try to change the constant radiative efficiency with different values, like 10 to -4 to 10 to -1, and we also see a similar trend as before, which can also be explained with the momentum arguments as before. And for cosmic ray, we also observe a similar trend, and we also put an argument about their momentum argument, but this is a different, because for cosmic ray we focus on pressure gradients, and but the pressure gradient is also proportional to the energy density when there's a ultra relativistic condition. So from this realization, we can see there's some very high energy bubbles which can insert additional pressure to the gems, to the material, and also expel the material away, and then reach this kind of radiation. So these are basically our results about black hole feedback. So I think one important conclusion for this one is that mechanical feedback is probably very important for halting this kind of hyper or super-Eddington accretion, and the radiative feedback is actually not very important, because when the feedback is when the accretion rate is very high, the photons from the black holes can actually carried or by the accretion flow to the black hole. So many of the radiation is actually suppressed. But the jet from the black hole can actually be ejected into a larger volume, which will affect the larger scale physics, larger scale status of the GMC, and in return it will regulate the black hole accretion. So these are some results, and also in the future we also want to try to do this project in more details, like we can do zooming simulations and to increase the self-consistency. And we are also happy to know to explore some kind of observational implications. So thank you so much.
Right, do we have any questions for the speaker?
Thanks for the talk. In terms of like the observational side of things, are there any prospects for, like, actually, how would you know whether or not you were looking at something that was accreting at such a high rate, especially given that you have these high densities and they're obscured, and if they're intermediate mass black holes, a mass estimate is going to be hard to come by. Basically, I guess, what are the prospects going forward for actually trying to find systems that look something like what you're trying to simulate?
Yeah, so I think I think you're right. So it should be also from our simulations and our estimations, we think that maybe the observational constraint is or implications is not very obvious in many ways. For example, first of all, we assume that this kind of accretion happens at very high surface density, which might be not possible in nearby galaxies, and they maybe only exist in proto galaxies, or and also very at a very early stage. And the second question is and we also assume that there's very high surface density, which means there will be very high opacity, which means that so making observations is not very hard, because there will be no higher or thicker optical thickness. And also the third point is about the star formation, because there are also very abrupt star formation events happening at the same time, so making it even less possible to distinguish the signal from this kind of accretion. Yeah, I'm not sure whether I answered your question.
No, thank you.
Any other questions?